Today's lesson is going to be on linearization and using tangent lines to make approximations. So first we want to talk about local linearity. Basically, it is what it sounds like. If a graph is differentiable, if you zoom in on the graph at a specific point, it's going to appear to be a line. So let's look at this. So take a look at this graph here. If you had to make a guess on what this would be, it's going to be a line, and it has a slope of about, let's trace. Okay, the x and y coordinates appear to be the same, so we could say this was y equals x. I'm going to zoom out. Okay, now it's kind of tapering off at the ends. Zoom out again. Okay, looking less and less like a line. Okay, so what we have here is the sine function. But when we zoom in to just one specific location, the graph appears to be a line. That definition included the fact that we need the graph to be differentiable. So here I've got the absolute value moved over to, if I want to trace to 2, we're here. If I zoom in now, we've got a corner. Still have a corner. No matter how far I zoom into this, this is not going to become the equation of a line. So we have to be differentiable in order for us to be able to get local linearity. We like lines because they're easy to deal with, and we can easily write the equations of them. So we're going to find the equation for the tangent line for y equals the square root of x at x equals 49, and we're going to use the tangent line to approximate the square root of 50. So let's go ahead and do the math here, and then we'll look at the graph and see what happened. Okay, so anytime we want the equation of a tangent line, we need a point and a slope. So the point is going to be 49 and the square root of 49, 7. The slope, y prime, is going to be 1 over 2 root x. So if I plug in 49, we get 1 over 2 root 49, which is going to be 1 over 2 times 7, or 1/14. So my tangent line approximation is going to be y minus 7 equals 1/14 x minus 49. I'll go ahead and add that 7 over. You don't necessarily have to do that, but I am. So now we're going to use this to approximate the square root of 50. Okay, so we're going to take 50 and plug it into the equation here. Okay, well this is just going to be 1, so this is going to be 7 and 1/14, which if you type that into your calculator, gives you 7.0714. Okay, if we actually do the square root of 50 in the calculator, okay, we get something pretty darn close, 7.0711. Okay, so we were accurate, fairly good. So what happened here? Okay, well if you picture the graph of the square root of x, okay, the graph looks like this. If I were to trace to 49, okay, we're here at that point. So I'm going to go ahead and draw add the tangent line. Okay, so I added the tangent line that we found, and if I graph that right on top, so we've got that there. So if I trace to 49, Okay, we're right there. If I zoom in on that spot, okay, the tangent line roughly represents the function at that point. So if I trace to 50, okay, it's super duper close to that line. So we're using the fact that really, really close, those values are going to be mimic what's happening with the line. Okay, now you'll notice numerically that our estimate was slightly bigger than the actual value. Looking at the tangent line, that should make sense because the tangent line is on top of the actual function. So what's making that happen? Well, it's happening because this graph is concave down here. So the tangent line lies above the graph. So if we have a graph that is concave down, our estimate is going to be an overestimate. And I kind of sketch a graph. It doesn't matter if it's increasing or decreasing. If our tangent line, if our graph is concave up, the tangent line is going to lie above it, so it'll be an overestimate. Okay, versus a graph that was concave up, if I had a concave up graph and I had a tangent line on it, okay, that tangent line is going to lie below the curve, so this is going to be an underestimate. All right, the chart below gives the rate of growth, h prime, of my daughter in inches per year. At 4 years old, she is 33 inches tall. So we're going to write the equation for the tangent line for her height at 4 years old. So I'm just going to use h as my variable. So h minus, she's 33 inches now, equals, our slope is going to be 5t minus 4. So h will equal 5t minus 4 plus 33. So we can use this to approximate how tall she's going to be when she's 5 years old. So 5 times 1 plus 33, we can predict she's going to be 38 inches tall when she's 5, so that'd be 3 feet 6 inches. Okay, now we're going to use the approximation, the tangent line, to approximate her height at 18 years old. Okay, if we do this, you get 103 inches. Okay, which is 8 feet 7 inches. Okay, so I want to use this to illustrate that, yeah, this is probably a reasonable prediction. My daughter being 8 feet tall, not reasonable. So if I go back to the graph that we were working with earlier, the farther you get away from this point, the less accurate that tangent line approximation is going to be. So if we're using tangent lines, we really need to stick close to the value that we're centered at. Okay, in our next example, we're going to find the equation for the tangent line for y equals e to the x at x equals 0. We're going to use that to estimate the square root of e, and then determine if that's an overestimate or an underestimate, and then we're going to actually find the square root of e in our calculator to confirm. So tangent line, we need a point and a slope. Okay, so y equals e to the 0, so that's just going to be 1. So our point is 0, 1. Our slope, y prime, is e to the x, so y prime evaluated at 0 is e to the 0, which is 1. So my tangent line is going to be y minus 1 equals 1, x minus 0. So if I simplify this, that's going to be y equals x plus 1. So on e to the x for values close to 0, I can use this equation. the square root of e is the same as e to the 1/2. Okay, so what we're interested in is plugging in 1/2 into our equation and seeing what we get. Okay, so our tangent line approximation is 1.5. Is that an overestimate or an underestimate? Well, if I look at the concavity of e to the x is always going to be positive, which means it's going to be concave up, which means our estimate is an underestimate. Okay, so if we actually calculate the square root of e, okay, we get 1.648. So this is slightly less than this. Okay, number 4, let f be a differentiable function such that f of 3 is 5, f prime of 3 is negative 1/2. The graph is concave up on the interval containing 3, so from 2 to 4. Find the equation for the tangent line at 3, use it to approximate 2.5, and then is it over or under? All right, so we have all the information necessary to do the tangent line. So y minus 5 equals negative 1/2 x minus 3. And since we're using it in a calculation, I like to add that y value over. Okay, so now we can use the line to approximate at 2.5. So it'll be negative 1/2, 2.5 minus 3 plus 5. So that's negative 1/2 times negative 1/2 plus 5, so that'll be a positive 1/4. So we're saying it's approximately 5.25. Okay, we don't have an actual function here, so we can't check it, but since our graph is concave up again, whatever this is going to be an underestimate. Okay, next from the 2010 AB exam. This is called a differential equation, and you don't really need to be concerned with what that means. But we have dy dx equals xy cubed. The second derivative is y cubed, 1 plus 3x squared, y squared. Okay, so we want to write the equation for the tangent line at x equals 1. Well, we already have our point is 1, 2. Our slope is always dy dx. So dy dx evaluated at the point 1, 2 is going to be plugging it in here. 1 times 2 cubed, which is 8. So our tangent line is going to be y minus 2 equals 8, x minus 1. Part B, use the tangent line from part A to approximate f of 1.1. So that's going to be 8 times 1.1, right, minus 1, plus 2. So 8 times 0.1 plus 2, so 0.8 plus 2, which is 2.8. Now, you could leave it just like this on the free response. Is our approximation greater or less than f of 1.1? So we're told f of x is greater than 0, and here, what we need to do is figure out the concavity. Okay, concavity is going to come from our second derivative. So I'm going to evaluate the second derivative at this point, which is going to be 2 cubed, 1 plus 3 times 1 squared times 2 squared. I'll clean it up a little bit, so this will be 8. 1 plus this will be 12, so 13, so 8 times 13, it's 104, but whether you know that exact value or not, we know it's going to be a positive number. So it's going to be greater than 0, which means this is going to be concave up again, which means this is an underestimate. Okay, so that's how we can use tangent lines to approximate values near certain other values.